Most language models don't reason. They simulate the appearance of reason extremely well. Early large language models are trained with one objective: maximize next token likelihood. Even when they solve complex problems, underneath they are doing fast pattern matching. But that is not reasoning. In cognitive terms, this is system 1 thinking: fast, automatic, and intuitive. That's exactly how early large language models work. But system 2, on the other hand, is slow and deliberate. It breaks problem into steps, it checks assumptions, and it reasons. The first idea was simple: if we scale model big enough, reasoning will emerge. With bigger models, more data, and more parameter. But scaling alone never produces true system to reasoning. Once pre-training hits its limit, the next step is supervised fine-tuning. Supervised fine-tuning adapts a general purpose model using labeled task-specific data. And yes, it does improve reasoning, but only partially. Direct fine-tuning teaches what answers look like, not how to arrive there. But the breakthrough comes with the chain of thought fine-tuning. Instead of training on answers, we train on reasoning trajectories. The model is explicitly encouraged to generate intermediate steps before producing the final result. Models don't just answer, they think through the problem. But supervised fine tuning is not enough, it has hard limits. First, data dependency. High quality level reasoning data is very expensive, that is slow to create and also domain specific. And second is catastrophic forgetting. Narrow fine tuning can erase general reasoning ability. And third is cost. Fine tuning large language models is still computational heavy even with parameter efficient methods. This exposed a very core limitations. Fine-tuning teaches correlation, not cognition. Scaling alone cannot fix this. For years, large language models were stuck in system 1. This pushed the researcher towards reinforcement learning, where instead of learning from level answers, model learn from reward signals through trial and error. In this framework, the language model becomes a policy. Its outputs are actions. Parameters are updated based on the rewards these actions receive. This is commonly implemented using algorithm proximal policy optimization. Reinforcement learning from human feedback trains a reward model from human preference to align with helpfulness and safety using PPO. But as human feedbacks are expensive, to reduce the cost, constitutional AI enables reinforcement learning from AI feedback that replace human feedback with principle-based self-critique. But direct preference optimization simplifies this further by optimizing policy directly from preference without an explicit reward model using pairwise preference comparison. But alignment alone still is not system to reasoning. The real shift happens when we stop treating reasoning as text and start treating it as a structured object. Instead of predicting answers, models predict reasoning trajectories. Intermediate steps become first-class objects, where the paper call it as thoughts. Once thoughts are explicit, they can be compared, evaluated, and optimized. Once thoughts are explicit, reasoning becomes a search problem. At each step, multiple candidate thoughts exist. Some lead to dead ends, others lead to solution. Now, instead of what's the most likely next token, the model asks which sequence of thought leads to success. This is where structure search enters and Monte Carlo tree search is introduced. Instead of sampling one chain of thought, the model explores multiple reasoning paths, evaluate them, and keep the only promising one. But such alone is not enough. The model needs feedback. Traditional training use outcome reward models that reward only after the final answer. But complex reasoning has many steps. Which steps were correct or which were critical, the model doesn't know. Researchers introduce process reward models that reward the process, not just the outcome, by scoring each reasoning step. It allows dense supervision, early pruning, and proper credit assignment. This turns reasoning into a skill that can be trained. Algorithm like GRPO optimizes step-level rewards. At this point, the bottleneck is not models, it's data. Reasoning models need high-quality reasoning trajectories. Traditionally, these come from humans, expert writing detailed step by step, token by token, and it is widely considered as high quality. But as models get stronger, the quality bar for reasoning data rises. They require terabyte of data, but constructing datasets through manual annotation becomes increasingly expensive and impractical. But leveraging large language models for data annotation provide a cost-effective and efficient alternative. This is where process reward models matter again. The first automation step is very simple. Use a stronger LLM to generate reasoning traces for training weaker models. This replaces human, but it also inherits the teacher's biases. Reasoning quality is capped by the strongest available model. So the next evolution removes imitation. Instead of asking for one reasoning trace, the model samples many. This is Monte Carlo reasoning with many reasoning paths, diverse failures, but few usefuls. The final step adds structure. Instead of independent samples, reasoning became a tree search problem. Monte Carlo tree search discovers high quality reasoning by reusing partial solutions and focusing compute where it matters. Data construction evolved from manual explanation to algorithmic reasoning discovery. Such algorithms prune poor reasoning early and amplify high quality trajectories with no human in the loop. The surviving reasoning traces become training data. This is the transition from human annotated reasoning datasets to LLM automated reasoning data pipelines, and it is the only reason large reasoning models can scale. Training doesn't decide everything, inference matters too. At test time, the model can explore multiple reasoning paths, allocate more compute, and search deeper when needed. This is test time scaling. Thinking become elastic. Chain of thought was the first upgrade where the model reasons step by step instead of answering immediately, but it still commits to one single path. One wrong step early, everything collapses. The next idea is very simple. Generate multiple chain of thought and take the majority vote. This reduces random errors and improves stability. But majority vote only looks at the final answer while ignores how the reasoning happened. So the beam search adds the structure. At each step, it keeps the k most likely continuations. Low probability paths are pruned early, but likelihood is not correctness. Confidently wrong reasoning can dominate all beams. Look at such as shallow planning, where the model briefly explores possible future continuations before choosing the next step, but computation grows quickly. PRM-guided Monte Carlo tree search unifies everything. Reasoning becomes a tree, not a line. Partial thoughts are reused. Promising branches get more explanation. Failed ideas are abandoned early. A process reward model evaluates each reasoning step during inference, but reasoning is cut immediately. Good reasoning gets more compute, no training updates, just better thinking. So large reasoning models are not just bigger LLM. They are systems that search over thoughts, optimize reasoning processes, learn from their own reasoning, and adapt computation dynamically. This is the shift from predicting text to constructing solutions, from system 1 to system 2, and this is the only beginning. Do you think reasoning should be learned at the training time or discovered at test time? Drop your answer in the comments. If this help you to see LLM differently, like the video and share it with someone who think bigger models mean smarter AI. And subscribe if you want more explanation that go beyond demos and into how this system actually works.